we discussed the first single writer, multiple reader, linearizable algorithm. So we start by using the same algorithm that we use to implement regular register. And if you remember, we had this idea of phases, and the phase consists of broadcasting a request and waiting for majority, and the phase ends when you get a response from a majority, and all other responses after that are ignored. And the write operation did an update phase and waited only for request from a majority, and that was it. You know this, you have seen this slide before. And the read operation did a query phase and picked the majority of the responses back. Also, you have seen this. That's why I'm going through it fast. So if I summarize the algorithm, it is like this now. We assume that the majority of processes are correct. We are in the fail silent model with using a timestamp, which is a sequence number, so it's a TS, and we have no failure detectors. So when you start to write, you increment the timestamp, you broadcast V and the timestamp to all processes, and if TS is higher or newer, this is the same thing, the receiver updates its local register value and it sends an ACK back. And when the process gets a majority of responses, then it ends the phase. So that is the return, and we return here. And to read, we do as before, a read query phase, broadcast read request to all, receiver responds with a local V and TS, and the process that started the query phase waits and saves values from a majority of processes, and once it does that, it picks the value with the highest timestamp. So this is the algorithm. We have seen that before, and we understand this. So now let us see if this algorithm works to achieve linearizability. And remember, we have a single writer. So we'll go through the algorithm by steps. In fact, what we are going to show now, this algorithm really implements a regular register, but not a serializable atomic register. And you can see this here. So P2 does an update phase with a sequence number 1, and it ends the update phase. So now, at this point, all processes have V equal 5. Let us see what happens with the next operation. So the invocation of the next operation, we have a write operation here. This will happen with sequence number 2, and it will do an update phase. So process 2 starts the update phase with sequence number 2. Process 1 starts a query phase. At this point, it will get from itself a value of 5. It will get 6 from process P2, and it will get 5 from process P3. It picks the maximum value, which is 6, and that is fine, no problem. Now the next event is the invocation of this read operation. So it starts the query phase, and it gets responses from itself with the value of 5, a response from P3 with the value of 5, and a response from P5 with the value of 5. Therefore, it will return the value 5. So this is the situation. So the algorithm as it is written now is not atomic. Why it is not atomic? Because this invocation is after this response. So this read operation precedes this read operation, but this returns the value 6 and this returns the value 5. So this returns an older value. So this is not linearizable. So let us look now how we'll solve this problem. So the main idea is called read impose or read update. So the idea when a process performs a read, it also do an update before responding. And let's see what happens then. So we'll see this case here. We are interested on this process. This process, after it gets the responses, it returns the value 6. But what it does after that, as you will see very soon, it starts an update phase. This update goes to a majority, P2, P3, and to itself, and it gets back responses from all of these. Now, this read that happens after the response of the previous read now will read this value as part of the majority it gathers. This will give it the value 6. From itself, we have 5 and 5 from P5, and therefore it will return the value 6. And as you can see now, the succeeding read, the read that happens, the second read that we see here, will return the value 6 instead of the value 5. So the first read makes sure that the write is complete before it returns. Therefore, a following read will return at least the value of that write that has been read by the previous read. So this is the basic idea of the algorithm. So let us look to the code. So the algorithm is as follows. The write phase is exactly the same to write the value. So we don't mention it, but the read has changed. And here is how the read works. The read works as follows. To read, you do a query phase, and now you collected a majority of values. Then you pick the highest one of these values, and you perform an update phase. Once the update phase is finished, you return the value. So that's it. This is the algorithm. It has two phases. So the read has two phases and the write has one phase. Now there is a small optimization here that you can make. So if all responses of the query phase return the same timestamp, do not perform the update phase, just return. The process knows that a majority has a latest value written. So this is basically the algorithm. Let us look a little bit why it works. The original algorithm without modification satisfies the validity condition. It is the same as in regular register. The extra update phase for the read operation, or the impose part of the read operation, actually satisfies the ordering condition here, which says that if a read returns the value R1 and that read is before the read returns the value R2, these are different values, then the write of R1 is before the write of R2. Remember, we have only a single writer. So as we said, a read makes an update with this value R1. And any succeeding read that comes after will either read R1 or a succeeding value. And therefore, we satisfy this ordering condition. So actually, we use causality to enforce the ordering. And by this, we enforce atomicity.